Thank you all for coming today. It's indeed a pleasure for me to introduce one of our talented PhD students, Egemen. Egemen completed his bachelor's in the Middle East Technical University in Ankara, which was, I would say myself, one of the top, if it's not the top school in Turkey in engineering, and came here and he did his master's, and hopefully this summer he will be completed his PhD. I think I will use this opportunity to mention one thing which is important about how to be a successful professor in the future. And I think that Egemen, he got what it takes to do that. Definitely, you need to be scholarly on the top, and he has been doing a great job as a scholar, and he published quite a bit, and he has been working on many different projects. And that's what I think gave him the background that will make him an excellent professor in the future. The second is teaching. He has been working, or at least he worked with me in a couple of classes where he was assisting me in teaching. And accordingly, he received the Mavis Award, which also trained him to be a professor in the future. The third one, which is the outreach and the service, and he did an excellent job in doing this. It's not by direction from his advisor, but mainly from within. So he will go ahead and offer workshops if it was like how to use MATLAB, or recently about neural network and so on. So it's all coming from within. In addition, he has been providing service to many technical committees, and he's always trying to be kind of like proactive when it comes to the service. So I cannot say more than that, except that I'm proud of him. I'm looking forward for his defense soon. So Egemen, or is it?
Professor, well, I'm not sure if my presentation can be better than that, like the introduction that you gave of me. So I really feel happy to be here, and well, thank you for all the kind words that you said. Today we'll talk about a project that we completed recently, and we are going to look at how these new autonomously connected vehicles are going to interact with our pavements. So let me give you some facts about freight. In 2019, we carried 73% of all of our freight using these heavyweight trucks. And that is a lot. That's like 11.4 billion tons. And they traveled 177 million miles, which is the distance to the sun and back. So if you got something just imagine that your package probably made it at some point in that duration, which I think is a lot of fun to think about. So since it is so crucial, even the smallest problems can be huge. And the things that I want to talk about are in here. We're going to talk about these 5 things for now. There is a driver shortage of currently over 60,000 people. And this is expected to get even higher and higher with time. 2, the cost per ton of freight is really high. It's approximately 3 times when compared to rail. So that's really huge. Third is the safety. The trucks make only 5% of the vehicle population, but they are responsible for 10% of all the fatalities. So again, that's something that we have to work on. And about the congestion, in 2019 alone, in a 50 miles segment, there was a congestion cost of $300 million. And then finally, again, as I just said, the 5% of the vehicle population consumes 24% of the fuel. And when you think about that, we are responsible for almost 1/3 of all of the emissions in the US. It's something that we have to look at. So at this point in time, I would like to introduce you the connected and autonomous platooning. So you saw the picture. What ends up happening is these trucks are following each other very closely and right behind each other. So with that, they save approximately 5 to 15% fuel. And this is because of their control strategies, because they can be really close, and one, they can really follow each other right behind the same line. And so the hope is that when we introduce the platoons, we are going to solve or actually reduce some of these problems. First is the driver shortage. You need just one driver per platoon in the first stage, and then you could even take that away. And it was calculated that this could actually reduce the costs by over 45%. And because the platoons are occupying less space on the lane, they actually increase the traffic capacity. And we hope that they also increase the safety. And finally, like as I just mentioned one slide ago, they save between 5 to 15% fuel. So it is looking good so far. But the one thing that we have not talked about is how are these platoons are going to interact with our pavements, because that's where they're going to be, right? So if you think about it, the reason why they save so much fuel is because they're really good at following each other in the same line. So in a very bad scenario, you were seeing a section from a test that you can have a scenario that looks like this, where you have damage that gets even faster with time because you keep loading the same point over and over again. And you may think, hey, this is a test section. It's impossible for this thing to happen in the field. Here's a picture we got from the field. You can see the same thing in small lanes that actually this is a thing. So we have to think about how we can solve this problem when we get into the platooning. So the one possible thing you can think of is you can say, well, let's shift these trucks to the left and to the right a bit, so that like over time, we're not loading the same point. And this will both save fuel and hopefully will preserve the payment condition, right? So we need a model that can describe this sort of behavior. So here are the four things, the four questions that we're going to talk about today. To know how does the platoons interact with the pavement, first we must know where can I platoon to begin with, right? What percentage of what segments of this highway can I actually do platooning? Two, how will this spacing change the responses and how the pavement is responding to the loading? And sorry, the third, how will this position where they are in the lane will change our pavement design? And finally, when we look at this in a whole life cycle perspective, is it actually reasonable for us to expect that platooning is good, or should we do something else? So well, these are the four questions that we're going to talk about in the remaining half an hour or so. So again, the platoonable segments, and then we're going to look at the impact of spacing, then the impact of lane position, and finally, we're going to look at the life cycle. So starting with the platoonable segments, when you think about platooning, we have to think about what is it that makes platooning save fuel. And the thing is that these trucks need to travel at a free flow speed for more than 15, 20 minutes for this to be feasible. If you have a lot of traffic and you have to stop and start, then it's not going to be fuel efficient. But two, you have to care about the rest of the traffic still, because if you have a very long platoon, if you think about it, right, and you want to take an exit, you don't want to fight with the platoon to take an exit, which can cause a lot of problems. So here are the two challenges that I just mentioned. The first is the vehicle density, right? If we have very high density, then I don't have control over my speed, so I cannot platoon. Two, we don't want a situation that can look something like this, right? You don't want a vehicle that wants to come into the roadway or get out of the roadway be stopped by a platoon. So with these two things in mind, we looked at the whole road network of the state. And for every 20-mile segment, we looked at these two things. One, what is the volume over the capacity of the roadway? And two, how many possible conflicts will there be within these 20 miles? And then what we did is we said, if it's a level of service C or below or higher, where you have control over your speed, then you can platoon. Similarly, if you are expecting less than 4 interactions between the vehicles, and then you can platoon. If you have higher, then you cannot platoon. So with this, you can see, for example, with 5 trucks with 65 feet of spacing, the majority of the network is platoonable, like except for Chicago, some red zones in Peoria, and a bit in Champaign over here, right? So then we did a sensitivity of this result. The picture that I'm showing to you here is at the peak hours. If you decrease the vehicle density, sure, you will have more sections that are platoonable, which again, makes intuitive sense, right? And again, the thing I showed you was for 5 trucks with 65 feet of spacing. If you have only 2, then of course you're going to be disrupting the traffic less. So the more percentage of the roadway will be platoonable. So that was the platoonable segment. So now that we know what percentage is platoonable, how do we actually change our design of the pavement to interact with the platoons, right? So the first thing we're going to look at is the impact of the spacing. So because we're talking about flexible pavements for now, and it's a viscoelastic material, we care about the time it takes for this material to recover once it's been loaded, right? So the fear is that if we put them too closely together, we will load the pavement before it fully recovers, and thus we will have cracking and rotting faster, right? So what we did to look at that was we run some finite element simulations, and we took these wood tires and we rolled them onto the pavement. And here is a quick video that you can see what that looks like in time. So what we want to look at, right? Once the first truck passes, the response, the stresses and the strains will recover a certain amount. And then if you bring in another load, you will have this loading profile. So depending on where you are on this path, you will potentially increase your responses, right? So if this happens, it might be the case that you're going to have faster failing of your pavement. So when we look at the finite element, and now I'm showing you the responses for the vertical compressive strains, we saw that almost like all of the responses fully recover within 0.15 seconds. And this is the distance for a truck traveling at 70 miles an hour to travel approximately 10 feet. So from this, we can say that if the distance is larger than 10 feet, then there is no impact of this on the pavement. But I have to put a star here because we have to realize that this is a finite element simulation. And at the end, what we're interested in is the stresses. So we are currently doing some tests on these permanent deformations, and you can see, well, this is not a final result, but we saw that as you increase the rest period, you actually increase your permanent deformation, which does not make a lot of sense when you first look at it, but I'm happy to talk about this later. But within the scope of what we did for the finite element, we did not see this result, but we're still working on it. So now that we dealt with the spacing and we said that it doesn't have an impact according to the finite element simulations, we have to look at the impact of lane position now. And I want to take a quick detour for the ones who don't know how we design pavements, because I think this will help kind of put things into perspective. So the majority of the roadways here in the US are flexible. So, and this is a typical structure of a flexible layer, a base, and a subgrade. So what you may want to do when you're designing your pavement is say, okay, so let me think about the most common load that I will have. And in the US, for example, this can be a class 9 truck. And then you take the most common loading on that truck, and then you put that in your favorite simulation software. It can be finite element, it can be something else. And then once you have that, you have the responses of the pavement, which are the stresses and the strains, right? And then what you do once you have that, you have this part, is you connect those to the stresses we see in the field, which is mainly the load related ones are the cracking and roughing, right? So this whole thing is called the mechanistic empirical pavement design, right? So where do we put the impact of spacing in this whole frame, right? So when you think about it, where it comes into place is that the point you shift the tire, the thing that's happening is you're also shifting this response. So if you can find a model for this shift, or if you know how that shift is happening, like, I guess how that shift is happening with respect to time, then you will have an idea of how this response profile will look like in, say, 10 years or 15 years, right? So how do we do that? If we have a case like this, where we have these trucks that are really good at keeping their position, then we can say that, well, they sort of follow a uniform distribution, right, with these 3 peaks. But then there is you and me, humans, who are in this roadway too, and we follow somewhat a normal distribution, which is what's shown in the literature. And then what you have to do is to just put these two up, put them together, which will give you, for like any mixture of the traffic, how the lane position will look like. And then if you want to see the future, let's say 10 years, 15 years, you can just compute the mean of this response profile that is subjected to this loading. Now, I know that was a little bit hand wavy, and I do see that. So let me show you a quick example here. So we have a pavement here that is 5 inches and a 6-inch base and a subgrade of 20 KSI. And we're going to load it with this pavement that is going to be a, loading with this truck that will be 1,000 per day, right? So the 4 traffic schemes that we're going to look at are the human, channelized, mixed, and the fully connected. And here is what that looks like. Stay with me. So this is what the human looks like, right? We're in the middle, but we're not perfect. This is what the channelized will look like. They're like always in the middle. Here's a mix of 40% connectivity, where we put 20% on the left side of the lane and put 20% on the right side of the lane. and then 100% in which we distribute it like this. So now we want to see what is going to happen in the pavement when we put these loadings on top of it, right? So if we look at the results for a span of 10 years, what we find is that, let's start with the permanent deformation. We have a baseline for the human. So like, as you might expect, if I impose a channelized loading, I'm going to have a lot higher rutting, right? But if I shift some of the traffic to the left and right, if I have a mixed regime, I can reduce this significantly. Now, I can do some further reduction if I distribute the rest, but we saw in these studies that it's a case of diminishing returns. So the first 20–30% that you shift really helps, but then the rest, it still helps, but like, if you can shift the first 20–30, you get a lot of the returns to begin with. So same thing with the cracking. We have a baseline for human, which channelized is worse. Mixed is of course better because we shifted it. And then we get a little bit more returns, but again, it's not as much as we had in the previous case. So the question that you might be thinking about right now, and I don't know if you are, is, well, is there a scheme that will actually make this as low as possible? And that was the question we looked at, and we considered a different amount of sublanes, and we placed these vehicles at these different locations with a genetic algorithm to see which one will give the lowest payment average. And for example, this is an example that a scheme that gives the lowest. But just to put it into perspective, the results of this is incredibly close to the one where we had one in the left, and then in the middle, and then in the right. Because think about how wide a truck tire is. Like, shifting this by ½ an inch is not going to really change your results. You have to shift it by a foot for you to see something that actually makes sense, right? So that's why you're seeing the impact of these diminishing returns, if that makes sense. So now we have that. Let's finally look at how does this all change the overall life cycle of this payment, right? And I want to take a quick detour to tell you what we mean when we talk about the life cycle, right? So when we talk about sustainability in general, we're talking about these 3 pillars. And for this project, we only focus on the first 2, but that's not to say that the social part is not important. It's just what we focus within the scope of this project. And when we talk about the life cycle, we are really talking about the point at which you have the material, your rocks and your binder, and how are you going to get them into the field? How are you going to get to them into the plant? All the way up to when you're done, how you're going to reuse or recycle your material. So if you look at a typical life of a pavement, you see that the majority is coming from the use stage, where the vehicles are interacting with the pavement to consume fuel. And the rougher your pavement surface is, of course, with the more fuel you're going to consume. So that's something that we have to keep in mind, right? So with this picture in mind, we did a life cycle assessment and life cycle cost for these 4 pavements. For the time, I'm just going to show you the results of this one, but it pretty much follows the same thing. I'm just going to show you one of them. And here are the 4 traffic regimes that we're going to compare for a span of 45 years, right? We have, again, the channelized, we have, again, the human, we have a mixture, again, of channelized and human, and we have one that where we distributed the traffic. Now, here is what the pavement condition will be like in a span of 40 years if you don't do any intervention. We do intervention a lot sooner than that. But you can see that the channelized one will be the worst pavement condition, the worst pavement surface. And the one that has the best pavement surface is, of course, the one that we were talking about, right? So if we look at the life of this over a 40-year life, and we assume that we're going to do regular maintenance at 10 years, 20 years, 30 years, and then 40 years, we can look at the impact of these costs. So when we talk about this, the agency cost is the cost that goes into building the roadway, right? So, and because I'm saying that we're doing maintenance at regular intervals at 10, 20, 30, 40, you would expect that this will be constant. And this is just for this scenario, by the way. We have some others, but again, for the time's sake, I'm just going to show you the results of this. Now, what do you think will happen to the user cost when we put that on top of this, right? So as you might expect, we have a benchmark for human. Now, when we platoon, when we are channelized, we are still saving a lot of fuel because we are platooning, right? We are saving fuel by platooning, and then the mixture is somewhere in the middle. But then if you actually distribute the traffic to the left and right, you are saving fuel, one, by platooning, and two, because the pavement surface is a lot less rough, you are consuming less fuel on the same pavement. So it's a really win-win-win situation. Like, you're not losing something in this scenario. So there's no reason why you should have channelized if this has the same savings and then more, right? So this was the result for cost. And if I put the total of the two, you see the same trend over here. If we look at the life cycle assessment, which is how much the energy we consume like over the lifetime, we see the same thing. Constant agency for this scenario, and then the same trends that channelized is good, but if you let me push these trucks to the side, we can save even more, right? So then we have this overall trend that shows us if we work on both the pavement damage and the fuel savings, we can have a lot more reduction in general. So for the time's sake, I'm just going to focus on these two. And in summary, what we showed, hopefully, is that by introducing what seems to be a challenge, we can actually turn this into an opportunity that will improve the freight in general. And we show that the a roadway's platoonability changes depending on the vehicle density and the number of interactions between the vehicles. And we developed a pavement design framework that can put these things into use and actually give you the pavement damage for a mixture of these vehicles. And then, of course, final but not least, if we have a scheme that works, we can reduce the costs and environmental impacts by 46% and 36% respectively, which is a lot when you think about it, right? So before I finish, I have to say thanks first to the Department of Transportation and CCAT, and of course, Dr. Alkadi and Dr. Uyang, who has been the PIs in this project, and all the students that are here. Well, they're here right now, and without them, it won't be possible. We all worked really hard in the last 3 years, and this is our collective work. So hopefully it makes sense to you, and I'm happy to take your questions at this point. Yes.
Can you go to slide 28? I'm wondering this approach compared to what MAPDG does.
Mhm.
So in MAPDG, we have a strain, we transfer it to the stress, then we accumulate the stresses.
Correct.
So how valid is it to accumulate strains and then transfer to the stress? That's the first question. The second part of it would be, how would MAPDG change if we were to use this or take advantage of this?
So the first question, I don't have the slides for that. But if you come to my defense, we'll talk in detail how that works. But in here, we're not accumulating the responses. All that is happening is this is a pavement response if I know where the load is, right? But in the field, I don't know where the load is. So it makes more sense to compute damage with that uncertainty than not. But at no point are we doing, we're still doing the same approach in which the damage is like accumulated and not the strains. In that framework, what they do in the tool is they divide this roadway into 5 lanes and they assign 20% traffic into those 5 lanes. And that's how they compute damage. Now, that's problematic because that's not happening in the field anyways, but well, that's what they're doing. And I think this is also approximately 50% faster than that approach. But like, that's a bit of a technical detail. And I'm not sure that answers your question. Yes. Angeli.
Thanks, Egemen. Really nice presentation work for slide 31. And also slide 38 for later. I noticed that at the beginning of the months, it's quite a steep, fast running increase, and also the IRI in the first months, like within 10 months. Can you explain why that is so steep?
This is a limitation of the rutting progression model. It is a power model, but it is dependent on the number of repetitions to a power. And if you plot it, what happens is you have, you get a lot in the first few months, and then it stabilizes. Is this what's happening in the field? No, but they fit this on the field data. So I'm thinking it's representative, but this is a limitation as we have listed of using these transfer functions on this framework.
Yeah, so I understand, but would it affect when it gets stable, right? So it doesn't matter how you get there. Let's say at the 25th year when it's stable, does it, if that was corrected, would that progression at a given year be impacted, or is it only that initial issue getting to that stability that's
So there is no stability per se. Like if you give this enough time, it will keep on going because it's a power model. So like it never reaches a constant. So I don't, by stability, do you mean where it turns from the primary to secondary? Yeah. I think that's a good question. So that is not, so again, this is going to be a bit of a technical answer, but if you plot this in the log space, it's just a line. So there is no distinction of like stability in that space. So when you plot it in that space, they're distinctly different. It's just that when you put it in this space, it looks like there is a distinction.
Yeah, I guess where I'm getting at, if I drew the curve more smoothly and not steep, but the rest is still fine, like progression over many months after, if that's not impacted, or that initial one. I guess we can talk later if you want, but I think that answers.
Yeah, sorry, maybe like I didn't know. Yes.
Can I comment on that?
Yes.
Yeah. I think this is the difference between rutting and cracking. In the case of rutting, you always have 3 stages, which is the first stage, the secondary, and then the tertiary. So what you're seeing here, because of the equations that they are using, you are seeing what's happening in the field. So in the field, you get significant rutting in the first 4 to 6 months because of the densification. And after that, actually, if you go beyond the 120 months, you may find the failure where it's going to go very, very steep. So this is representative of what you are seeing in real life, actually, because of the equations that they are using for the rutting. But if you look into the cracking, on the other hand, the cracking is usually very, very slow, and then it will be increasing. So if it extends beyond the 120 months, then you will find that it will increase significantly when it's developed. So I don't think that there is a problem with the figures.
Okay, and then on 38 for IRI, it's also steep. Is that also?
The transfer function for this is a function of rutting, and so it follows a similar trend.
If I may, I mean, the IRI is calculated from the fatigue and the rutting equations, so that's why it's reflected here too.
Thank you.
Sorry.
I just have a very basic question. How is truck platooning better than the railroad freight? I mean, in
I don't
truck,
think we compared the two. I think that's a good, like, are you like asking if we should do more like rail
so
instead
the
of?
first thing is that I guess that the platooning thing is quite new, right? And we have to deal with the autonomous trucks and also the pavement stresses. These are the main things that we have to deal with. While the freight railroad is already set up, I mean, why would someone select this thing rather than using the setup thing which we have? The question that I have.
Yeah, well, that is a great question that is way like out of my expertise. Like, you want to know why we don't do more rail, right?
Because the thing is that
yes.
I watched the video yesterday about I guess Marcus Brownie posted it, and he talked about how some of the electric driving vehicles project like Faraday was there. They all like are very bright, but then they don't get any investment or funding, and then they just go down. So how do you think that this project will scale over time?
When you say how will platooning scale
Yeah.
over time?
How can
So,
you like, make it work?
Platooning is happening, like it is happening like right now, and there's a lot of like interest because of the reason I said like 73% of the freight is carried on trucks. But you want to know, I think, if that's too high, like should we do something to reduce it to do even more? And that I don't think I'm qualified. I mean, I fully see your point, but I can't comment on that part of it.
Actually, I see where Elijah is coming from. The rail has always the certain channelized traffic, right? And I think you've done a very good job in your presentation showing, if we stay channelized, how we do much more damage. That's really the one end of it, and then the other one is like you're bringing the two together and mix them. So I think from a damage perspective with these functions, it makes sense. But where I was lost a little bit towards the end was when you brought some of this, because this is the use phase in your LCA, LCCA calculations, right, at the end. But you had an optimized one that was actually even lower than the lowest case that could be achieved. How did you get to those optimum cases that you could actually, towards the end, the very last pictures, the optimized, how do you get the present cost to be much lower than, even the channel or the mix?
Right.
Because if you look at the damage, you have the highest and the lowest and in between, right? So those cases really govern the first three bar charts there. The fourth one is now you're pulling things further down.
Yes.
How does that happen?
So to answer that question, let's just look at the channelized and optimized where we have 100% penetration. So those two are comparable. If we look at the pavement condition, because this one has a lower pavement roughness, we are consuming less fuel because the pavement is less rough. And this is coming from the models that we developed previously that connect the pavement roughness to how much fuel we consume.
So actually, your optimizer, you put that even well below that the human one, right?
Yes, the human is our benchmark. Yes, but yes, we can lower it further. We can lower it further than the human.
With the Platoon.
Yes. And in here, what ends up happening is we channelize, even though it has higher payment damage, it still has better user cost because the savings of the fuel, but they are still consuming more fuel from the payment roughness point of view. But then we move into here where it's the best of the two. I have less fuel consumption from the payment and less from the Platoon.
So it may help to bring those aspects that contribute to this final result to actually show how they just relate to each other or affect each other. Okay.
Yes, thank you.
I have two small questions, if that's okay. Can you go to the IRI progression curve? Don't you think it's a little bit strange that after 40 years, the maximum roughness is only 100 inch per mile?
Yes. No, and the reason I'm saying no is because let me explain how this is calculated. So in the way we calculate it, this is a function of payment rotting, fatigue, and then there are the conditions that are due to thermal loading. Now, because there is no difference in thermal loading between the two cases, like if you have platooning or if you don't have platooning, we are assuming that it's the same. Whatever contribution is coming from the thermal is subtracted from this. So this will be higher if we included thermal, but we didn't want to put thermal where it doesn't belong. So we just wanted to
I see.
compare.
My other question is related to the first task, where you decided which sections are platoonable and which are not. So I noticed that in that map you showed, there would be like very long platoonable sections, but then like a small dot that is not platoonable. Well, I was thinking that maybe at these locations, the platoon would have to split up, like the trucks would have to split up. But then you would lose the saving, like you cannot do this with only one driver. So this advantage that you were talking about to only have one driver or something is not going to be possible. You would still need 5 drivers for the 5 trucks to be able to split up and come back together or stuff like that. Do you have any ideas of how to make those small segments platoonable?
I think that's a good question. With regards to your first thing you said about having one driver.
Sorry.
Well, there have been some tests that show that you can only do one driver, even with a spacing of 250 feet, where the vehicles come in and out and the trucks are still able to follow. So it is technically possible that you can break the platoon with only one driver and then still bring it together. So it is technically possible from the things that I've read. But your point is very well taken, is that like, if I want to go from here to here, I really need to think about like, is there something I can do to make this platoonable? And I guess the simplest thing you can do is to wait after 5 p.m. for example, to like do it at a time where you can platoon, where you can calculate how much fuel savings you are losing by not platooning here during the peak hour and compare that to your loss of time, which can give you like another proxy. But I don't have a concrete answer for you. Like, what can we do to make this platoonable at this point? Yes.
Thank you for the presentation. I just wanted to get your opinion on how this platoonability and platoonable trucks, how would they affect the traffic at the terminal stops of these platoons? If that makes sense.
What do you mean by the?
So, say for example, in Chicago, where they have a multimodal node where all these platoons are coming in. presently, when there's no platooning there, the traffic characteristics are a little bit different. So in your opinion, how would this affect that traffic flow? And whether we need to like make some adjustments there?
So if I understood it correctly, platooning is not a first and last mile solution. It's more like a middle mile solution. So when you reach those points, you already don't have a platoon. How it works is when a truck enters the roadway, it looks to see if there are other trucks that it can platoon with, and then they form a platoon, and then they follow the route until one of them takes an exit. So you don't have a case where 5 trucks leave here and they all go to Chicago together. It's more of like they all find each other on this way. So for the platooning side, I don't have any answers for those first and last miles, but we have a project right now that we're working on how to use the drones to help with that first and last mile thing. But that's not a place where we can put this framework in.
Right. You have the last question.
Okay, have you thought about how, for example, IDOT would implement this in particular? Do you envision signs that are telling you can platoon as of here until here, like speed limits, or something different?
Yeah, they had the same question when we presented this to them. I think the solution we came up with at the time is how you would calculate the fees. If you say, I want to go from here to here at this point, like they have their own network, and then it says, okay, you can platoon from here to here and then not here to here. That's what we thought about when we were pitching it to them, is it's on the network, and you say, I want to go from here to here, and it will tell you where you can platoon.
I'm not following.
Sorry, which part was confusing? I'm sorry.
So if I'm the driver of
Yeah.
a truck, how do I know where I can platoon and where I cannot?
Well, you know your destination and where you start from. So you put that into your system, right? You were in the THE, they have to input information into their system to know where they're going, and that system can tell you where you can and cannot platoon by doing this calculation.
All right, Egemen, thank you again. We appreciate it, actually.